Welcome back, guys. Today I'll be doing mathematical induction, proving that the summation from 1 to n r times r minus 1 is equal to n open bracket n squared minus 1 all over 3. Let's get started. Here, using the method of induction to prove that the left-hand side is the same as the right-hand side. So first, I'll be proving when n is equal to 1. When n equal 1, it means that I am substituting 1 into both sides, and I should get the same answer for it to be correct. So when n equal 1, I'm testing to see if the left-hand side is the same as the right. So I replace r with 1, although I say n equal 1. Remember, the summation is from r equal 1 to n. So n now is being replaced with the number 1. On the right hand side, I am going to also replace n to be 1. So I have 1 open bracket, 1 squared minus 1 all over 3. Calculating this, 1 minus 1, that's 0. So this part will be 0. So you know 0 times a number, it is just 0. Numerator, 1 squared is 1, so 1 minus 1, that's 0. 0 times 1 is 0. So in the numerator I have 0 and the denominator is 3. So 0 over a number is 0. So here I've proven that the left hand side is the same as the right hand side, and it means that it's true for n equal 1. Now we have to prove for n equal any number. So let's assume that it is true for n equal k. So the next step is to assume true when n equal k. So n equal k means that we're going to sum from 1 to k. So the stopping point is at k. So where I have n at the top, the upper limit, I am going to change it to k. It is the same scenario on the right hand side where I am going to replace the n, the letter n, with k. So I have k open bracket, k squared minus 1 all over 3. So this is saying whatever is k could have been 5, 6, 7, it is true. That's an assumption, it is true. So it means if it is true for this number, then the next number that follows, it will also be true. So if it is true for n equal 5, then it will also be true for the next number, which is n equals 6. So that's what we mean by k plus 1. If I assume that is true for this, then the next number will be true because it relies on the previous information. So it means the summation, I will have r equal 1 to k plus 1. Then the remaining r, open bracket, r minus 1, close the bracket, is equal to replacing this n with k plus 1. So I'm going to have k plus 1 times k plus 1 all square, because this is n squared, so replace it. I will have k plus 1 all square minus 1 all over 3. So the idea is to get the left to look like the right. So I am going to prove that the left hand side is the same as the right hand side. Let's look at the right hand side. For the right hand side, I am going to rewrite it in a different form. The k plus 1 all square, it means k plus 1 times k plus 1. That's what k plus 1 all square means. So I can expand this. So expanding it here, k plus 1 all square, I will multiply k times k, that's k squared, k times 1, that's k, and then 1 times k, that gives me k, and 1 times 1, that gives me 1. So adding the center, that would be k squared plus 2k. So k plus 1 all square is the same thing as k squared plus 2k plus 1, and then here I would have my minus because this is k plus 1 all square. Still k plus 1 all square, but being expanded, then we have minus 1. So beside it, I will have my minus 1 there. Now, putting the minus 1, you should be seeing that I'm going to have a cancellation. The plus 1 and the minus 1 will cancel. So I can go ahead and cancel the plus 1 and the minus 1 that I have there. So my next line, I will have k plus 1 and the 3, but the remaining section I will have k squared plus 2k. And I'm going to put this in bracket, so we have two brackets being multiplied. Now k is common and I can factor out a k, so it means that here I will have k, open bracket, factor out the k, I'm going to just k plus 2. So I'll have k plus 2 all over 3. So this is the same thing as, since it's in the denominator, it's the same thing as 1/3. Then I can write the k first, followed by k plus 1 be multiplied by k plus 2. So this is what I'm going to get for the left hand side. I'm working towards getting this on my left hand side. I like to start off with the right hand side, then I move to the left hand side. For the left hand side, I can split this summation from 1 to k plus 1. So it will be the summation from r equal 1, and I stop at k plus the k plus 1 term. So the left hand side, we split it summation from r equal 1 to k plus the k plus 1 term. Why is that the case? Let's think of numbers. Suppose I have the summation from r equal 1 to 5. So I start at 1 and I stop at 5. Let's put r squared. Just a random example. Now this means I can split this to be the summation from r equal 1 to 4, r squared, plus the fifth term. Because when I merge this together, it is still saying summation from r equal 1 to 5. So this represents the same thing. Even though I've split it, it doesn't look the same. So if I change the upper limit from 5, so from r equal 1 to 5, so I have it as 7, then it means I can split this from r equal 1 to 6 plus my 7th term. So splitting this, it's still saying summation from 1 to k. Now the first part is the assumption that was made. So summation from 1 to k, I will use the assumption that I have here, assume true for n equal k, and then the k plus 1 term will be, we'll get that from r times r minus 1. So this part will replace the summation from r equal 1 to k, because the assumption says that is equal to k, open bracket, k squared minus 1 over 3. The term I will have to replace here to get the term. If I wanted the fifth term, that's where I would have replaced it. So I replace r to be k. So wherever I see r, I replace it with k. So it means cancellation happens here because the plus 1 and the minus 1, it cancels. So canceling this, I'm just left with k times k plus 1. Now because I have a fraction, I am going to put this all over 1 because it means I'll have to find my LCM. So the LCM for 3 and 1 is 3. So 3 into itself goes 1 times. I just get back the numerator, which is what I'm writing. And then the next side, 1 into 3 goes 3 times. So multiply this by 3. I will have 3k times k plus 1. Not 3k times 3k plus 3. No. 3k times k plus 1. Now this is difference of 2 squared. K squared minus 1. That is difference of 2 squared. So I can rewrite this to be k plus 1 times k minus 1. So that is difference of 2 squared. And then the next part, I will just have as is, which is 3k times k plus 1. Then it's all over 3. Now, k plus 1 is common, so I can factor out the k plus 1 that I have here. And factoring it out, what is remaining? I will have k times k minus 1. So we have the k times k minus 1 plus 3k. Now, this part I'm going to complete on the next page. So continue with the left hand side. I'm going to expand here. So k times k minus 1, what does that give me? I will have a k square minus k plus 3k. Next, I can simplify further. Minus k plus 3k, that's 2k. So my next line, I will have k plus 1 times, I'll have k squared plus 2k. Now, k is common in this. It should be seen that k is common. So it means I can factor out k that is common here. So factoring out k, I'm going to put it in front here. I'll have k plus 1, and then we will have k plus 2, because I factor one of the k's, so it means it's no longer k squared plus 2k, but k plus 2. Now looking at this, it's actually the right hand side. If I put the 130 in front, you're clearly seeing the right hand side. So I have now proven that the left hand side is the same as the right hand side. And since they are the same, we can draw a conclusion. So the conclusion is that we're proving for all numbers, and it has shown that it's true for all numbers. Since it was true for when I substitute n equal 1, I got the left hand side to be the same as the right, so it is true. I also assume true when n equal k. So this was an assumption that it's already true for n equal k. So from this information, I am able to determine if it is true for the next term when it is k plus 1, which I have proven, so I can say, and it is true for n equal k plus 1. So since it is true for n equal 1, assume true for n equal k, and proven true for n equal k plus 1, then this is telling me that it's true for all positive numbers from n equal 1 to k plus 1. It is true for all positive numbers, and it means starting at r equal 1 and stopping at n, whatever the positive numbers are, it is true for those values, and I've just proven that. Thanks for watching, guys. Don't forget to like and subscribe to my channel. Have a great day.